Hey everybody! This screencast is about how scientists have determined chemical formulas from various analyses. We often take chemical formulas for granted. Everybody knows that water is H2O. But how have scientists determined formulas for different compounds? How do we know that water is H2O or that glucose is C6H12O6? Scientists have figured chemical formulas out by reacting substances or decomposing them, breaking them down, and have been able to measure the relative masses of the various elements within a compound. We know from the law of definite proportions that the relative masses should always be the same for any compound. If the relative masses are converted into relative numbers of moles or atoms by using the periodic table masses, the formula for the compound can be deduced since a formula tells us the relative number of atoms within any given molecule. For example, in water, there are always 2 atoms of hydrogen to 1 atom of oxygen. Here's an example. A scientist was able to decompose an unknown substance into calcium, carbon, and oxygen gas. She obtained the following data. Because the formula is really a ratio of the number of atoms of each element in a compound, instead of mass, we need moles. Convert the relative mass of each element into a relative number of moles. Pause this video and try this now. This is what you should have calculated. By using the masses given in the table, we can use the periodic table mass to convert how many moles there are. This question on the bottom says, is the relative number of moles any different from the relative number of atoms? Take a minute to think about that by pausing the video. The relative number of moles should not be any different from the relative number of atoms. Since a mole is always 6.022 times 10 to the 23rd atoms, the relative number of moles should be the same as the relative number of atoms. So now that you've gotten the moles for each of these elements that were present in this unknown compound, we can now find the relative ratio. So using these moles, determine the whole number ratio of each element. In other words, what is the ratio of calcium atoms to carbon atoms to oxygen atoms in this compound? So pause this video and see if you can figure out how we're going to find the whole number ratio for this. Think about the lab that we did and how we found the ratio there. If you need a hint, you need to divide the moles by the smallest number so that we can see how many times each one of those moles goes into each other. As you can see here, I chose the average of these two because these 2 moles of calcium and carbon are really similar. Maybe if you'd only gone to 3 sig figs, they would be the same. I just averaged them, but you could really use either one of these and your answer would not be any different once you've rounded for your final answer. So by dividing by the smallest number, we see that this divided by itself is 1, same here, and when we divide the moles of oxygen by this smaller number, we end up with 3.00, or 3. So this means that there are 3 moles of oxygen for every 1 mole of carbon and 1 mole of calcium. So if we're going to write this into a chemical formula, we're going to write CaCO3. Notice that the 1s are assumed and not written. Percent composition tells us the relative mass of elements using percent values instead of grams. The percent composition is what the mass of each element would be if the sample size was 100 grams. Sometimes it is helpful to find the percent composition of a compound to compare it to data, and other times you're going to be given the percent composition and need to use it in problems. We can think about percent composition through an example. A 100-gram sample of a compound is decomposed, and it is found that 40 grams of the compound are sulfur and 60 grams are oxygen. This means that the compound is 40% sulfur by mass and 60% oxygen by mass. Try this problem on your own by pausing the video. Here's what I did. I took the 5 Pomeranians, multiplied by their mass per Pomeranian to get the total mass of Pomeranians, and then used that mass and divided by the total mass, multiplied by 100 to get the percent. So if we were going to think about a general formula, if you haven't done that already, go ahead and pause the video and think about what our general formula for finding a percent composition is. I would say that the general formula is looking at the mass of what we're trying to find the percent composition of, in this case Pomeranians, divided by our total mass times 100. Using that idea, find the percent composition by mass of oxygen in baking soda. Pause this video and try that now. Here's my work. If we find the mass of oxygen in 1 mole of baking soda, we know that there's actually 3 moles of oxygen atoms in that whole mole of baking soda, or sodium bicarbonate. So 3 moles of oxygen, 1 mole is 16 grams, gives us 48 grams of oxygen atoms for 1 mole of baking soda. We can use the masses on the periodic table to find the mass of the entire baking soda molecule. This is called the molar mass. Then, to find the percent oxygen, we can use that mass of oxygen and divide by our total mass, multiply by 100, and we get our percent. This problem is a nice one to use because baking soda has a mass right around 100 grams. So if we go back to this other problem, an unknown substance is analyzed and found to contain 35% sodium. Is this unknown substance baking soda? You could mathematically go ahead and calculate what sodium's percent composition is for baking soda, or we can see here, since our total mass was 100, baking soda's got to be right around 22.99, which is not 35. So no, that is not baking soda. Go ahead and pause this video and try to solve this problem on your own. Think about, if we have percent compositions, how we can get that 2 grams to start this type of problem. Okay, so we need to first find out what the other percentage is. We know that this compound is made up of only iron and oxygen. So if oxygen is 30.1%, iron must be 69.9%. When we have percentages, it really doesn't matter what our sample size is. Because of the law of definite proportions, if we had 1 gram, or 10 grams, or 13.7 grams, or 100 grams, the relative percents of each would be the same. So let's assume we have a 100-gram sample. That makes our math a lot easier. If we have a 100-gram sample of this compound, that means that 30.1 of them have to be oxygen and 69.9 grams have to be iron. Now we're going to go through that same process and take our grams and convert that into moles. We cannot find relative ratios using grams because atoms weigh different amounts. A whole mole of oxygen atoms weighs 16 grams. So by converting the grams of oxygen into moles, we get how many moles of oxygen are present in this 100-gram sample. We can do the same thing for iron using its mass from the periodic table to get that into moles of iron. These moles here represent how many moles of oxygen and how many moles of iron are present in this sample. Remember, we didn't care about the sample size. We're really just trying to find relative ratios. So by dividing by the smaller number, that's going to help us to see a cleaner number of what that ratio is. So by dividing by the smaller number here, we see that we have 1.5 oxygens to 1 iron. We can't use decimals in a chemical formula, so we need to multiply this by some whole number to get them both into whole numbers. In this case, we can multiply by 2 to see that 3 oxygens exist for every 2 irons. This would result in a chemical formula of Fe2O3. Don't worry about the order in which you're listing your atoms for now. In general, it goes from left to right on the periodic table, but we'll be talking about that more later. All right, I'll see you tomorrow in class.